You know, we usually think of foresight as, well, a human thing. But what if our machines had it too? What if they could just tell us, hey, I'm about to break, long before it actually happened? Well, that's not science fiction anymore. We're talking about a kind of digital crystal ball for the engines and the systems that power our entire world.
I mean, just really think about that for a second. What if a bridge could send out an alert before a critical weakness even starts to form? Or what if a jet engine could signal a potential problem weeks, maybe even months, in advance? The stakes of an unexpected failure are just incredibly high, and they affect everything from our personal safety to the whole global economy.
Well, that kind of technology is actually already here, and it is totally transforming industries. It's called predictive maintenance, and it's basically like giving our most important equipment a sixth sense. So let's pull back the curtain and see exactly how this thing works.
So, first things first, what's the actual problem we're trying to solve here? Well, the core challenge has always been that machines can be unpredictable. When a really essential piece of equipment suddenly breaks, the costs aren't just in the repair bill. No, the real cost is in the unplanned downtime, which can stop an entire production line in its tracks and, in some cases, create some really serious safety risks.
And that's where this idea comes in. The big shift is moving from being reactive, waiting for things to break, to being proactive. Predictive maintenance is all about using data to spot weird anomalies and potential defects so you can fix them before they turn into a catastrophic failure. It's basically trading a wrench and a guess for data and a forecast.
It all starts with listening. I mean, before you can predict anything, you have to learn the language of your machines. This first part of the process is all about capturing those really subtle whispers and signals that tell you what's truly going on inside. And this whole process works kind of like a data pipeline with three main stages. First, you gather the raw signals using sensors, things like vibration, temperature, electrical currents. You can think of this as a doctor putting a stethoscope on a patient. Then, step 2, you've got to clean up all the noise. Raw data is messy, right? So we use these advanced filtering techniques to cut through all the background chatter and find the machine's true heartbeat. It's like panning for gold in a river of data. And finally, we isolate the key features, what the experts call health indicators. These are the specific patterns that tell us if a machine is healthy, if it's under stress, or if it's starting to degrade.
And the difference is just night and day. On the left, you've got the raw sensor data. It's chaotic, it's noisy, it's pretty much impossible for a person to make any sense of it. But after all that processing, look at the right. You get this clean, rhythmic health signal. It gives us this really unambiguous look at the machine's true condition. We've literally turned noise into knowledge.
Okay, so we have this beautiful, clean signal. Now what? Well, now we need something that can actually interpret it. And that's where our digital detectives come in. These are these super sophisticated machine learning models, and we train them to hunt for the hidden clues of an impending failure inside that clean data.
And just like real detectives, different models have their own unique styles. For your more common, everyday tasks, like analyzing vibrations in a standard bearing, you might use a tree ensemble model. It's fast, it's decisive, it gets straight to the point. But for the really tricky cases, like a super complex system and a jet engine with data streaming from hundreds of sensors, that's when you bring in the big guns, the deep-diving neural networks, which are absolute masters of recognizing complex patterns. And then, for forecasting the future, you've got your specialists, the time series models that are designed to understand the past to predict what's coming next.
And this is a really important point. As Abia Bendit put it, there's no single magic bullet here. Choosing the right detective is always a careful balancing act. You're constantly weighing accuracy against speed, cost, and, how easily you can actually understand the model's conclusions.
So, our digital detectives have been trained, they're on the case, they're sifting through the data. Now comes the moment of truth. What are they actually looking for? Well, it all boils down to two critical predictions that let us see the future.
And here they are. First up is anomaly detection. This is what tells us if something is wrong right now. A sudden spike in temperature, a weird vibration, anything that deviates from the norm. It's our immediate alert system. But the real game changer is the second one, predicting the remaining useful life, or RUL. This is where we go from what's wrong to forecasting when a component is likely to fail in the future.
And let's be super clear about this. Remaining useful life is the holy grail. It is the #1 goal of this entire field. It's the estimated time a piece of equipment can keep operating before it absolutely needs to be repaired or replaced. It's the difference between knowing there's a problem and knowing you have exactly 3 weeks to get it fixed.
So how is this RUL even calculated?
Well, it's not a single snapshot in time. The models are constantly analyzing those health indicators we talked about, tracking them minute by minute, hour by hour. They are literally charting a component's slow and steady decline, from perfectly healthy all the way down to critically faulty.
And this is what you get. Not a vague warning, but a concrete, actionable number. The system doesn't just say, the bearing seems to be wearing out. No, it says, this bearing will likely fail in 150 operating hours. Now you can plan. Now you're in control.
Okay, but a prediction is totally useless if you don't do anything with it, right? So the final, crucial piece of this puzzle is creating a totally seamless link from that digital alert to a real-world solution so you can avoid a crisis altogether.
And making this happen on an industrial scale takes some serious technology. You can think of it as a three-part backbone. First, you need intelligence on the machine itself. That's edge computing, so you get instant alerts. Second, you need super reliable networks like 5G to connect hundreds of these machines without any lag. And third, you have a hybrid cloud system that acts as the central brain for all the heavy-duty analysis and for plugging all this information into the company's other tools.
So here's how it all comes together in a completely automated workflow. Step 1, the prediction is made. Our bearing is going to fail in 150 hours. Instantly, an alert is automatically sent to the maintenance software. No human has to do a thing. Then, that system automatically creates and schedules a work order, which all leads to the ultimate goal in Step 4. The part is replaced during regularly scheduled maintenance, which means zero unplanned downtime, zero interruptions.
And the impact of this is just massive. What you're seeing here is the before state. Without this tech, companies are just constantly battling high unplanned downtime, crazy expensive emergency repair costs, all of which leads to low overall availability. For a big factory, avoiding just a few hours of an unexpected shutdown can save millions of dollars. This tech fundamentally changes the game.
Which brings us to a final, pretty fascinating thought. This technology gives us an absolutely incredible ability to see the future for our machines, to predict their breaking points with more and more accuracy. So the big question is, as we get better and better at predicting failure in our complex mechanical systems, what else could we learn to predict next?